we'll see how we do with the background noise, but I wanted to show you a system that was built to keep livestock watering tanks from freezing. As you can see, the solar collector is below the level of the stock tank, has a fence around it to protect from livestock getting into the collector area. And then hot air rises naturally and moves through rock, which can be put over insulation to go all the way with the possibilities here. And then another thing that can be done is to augment the escape or the draw of air through the system by painting a stovepipe flat black on the south side if you're in the northern hemisphere. So you're really heating rock during the day to release the heat through radiant energy all night to keep the water from freezing for the animals. This concept of heating below the area you want to keep from freezing is also perfect for a raised bed that could produce vegetables all winter long, even without glazing. So this is the third part of the San Luis Valley Solar Energy Experience videos, and I thought I'd share with you some things from news, what we call the solar flashes. This is an edition called the Solar Air Collectors, a design and construction guide, and this information is available for free through the Heart Mind Alliance and also through Northern New Mexico College that has this information archived. It's important in designing a solar collector, especially to be aware of collector temperatures. The collector should be around 110 to 120 degrees Fahrenheit at the delivery of hot air. If it's hotter than that, you can imagine the air heat escaping from the glazing increases, because the more the differential between the heat inside the collector and the outside cold, the faster the heat loss. So delivery temperatures aren't as effective in keeping a house warm in that case. A cool collector is an efficient collector because there's less heat differential between the collector and the outside air, and therefore less heat transfer and loss. To achieve that, at 7,500 feet, which is the altitude of the San Luis Valley, the collector fan should move 3.5 to 4 cubic feet per minute of air per square foot of collector through the system. At 5,000 feet, a fan should move about 3 cubic feet a minute per square foot of collector, and about 2 to 2.5 cubic feet per minute at sea level. This is due to differences in the density of air at different elevations. So this kind of information is important. Why orientation and tilt is important to take into consideration. Most of our solar collectors are vertically mounted so that in the summer the angle of incidence of the sun simply doesn't allow the collector to even come on. Here are different airflow patterns through collectors. Here's a double ducting system splitting off to get the cold air from two different panels and to deliver the hot air from two different panels. We have materials lists available. I wanted to show you the type of fan which is used, which is called a squirrel cage fan, where the motor stays out of the airstream. You don't want the motor heating up with the hot air from the collector. And here you can see a vibration collar so that the sound of the fan doesn't move through into the house. Backdraft dampers are a good idea because they close as soon as the air stops moving, and it prevents heat loss from the collector at night by what we call reverse convective flow. Here's the all-metal collector, which we moved to. We did this after the first collectors that were 2x4s and 2x2s inside began to char with the heat and deteriorate, and so we went with C-channel, which you can see there, either coming out away from the plywood backing or actually coming in to create a true C. Here you can see a smaller C inside, another one to hold up the absorber plate, and so this was actually simplified with the Willett design, which we'll be able to take a look at. Controls, a simple attic fan differential thermostat works, where the probe inside the collector reads how much temperature there is inside the collector and turns on the fan when the collector is hotter than the area you want to heat. As soon as the collector cools off, so it's cooler than the area you want to heat, then it turns off automatically according to preset temperatures. So here's another simplified cross-section of a collector where one C-channel inside here, inside the insulation, holds the absorber plate, and the other one up above holds the glass. Here's the wooden systems that we used to build. We don't recommend. Here's another cross-section of a solar collector. Here's a whole section on static pressure, rules of thumb for duct sizing, which you could pause if you need to check that out, and fan selection size. Static pressure is a measure of the resistance to movement of air forced through a system. It's measured in inches of water. Cubic feet per minute is the volume of air moved per minute. Static pressure is dependent on the length and size and configuration of the ducting. It says that its static pressure will be low, preferably under 1/2 inch. If the ducting is extensive, small in cross-sectional area, and has many abrupt changes of direction or very high airflow through it, it will have a higher static pressure and less delivery of heat. So here's some calculations on static pressure. Here's a two-mode system diagram where backdraft dampers are used. Heat in this case will go into the house furnace. We can also set up so it's a simple closed loop to heat water, for example. Here's a water heater. This one had a spiraling ductwork installed on it, but we also had what we call the porcupine tank, which you can see in the San Luis Valley Solar Energy Experience. We photographed some of the porcupine tanks. So got a lot of interesting experience, learned a lot over the years in the San Luis Valley of Colorado, and we're happy to share in any way we can what we learned and what mistakes to avoid.